So hello guys, welcome back to the Linux Troubleshooting Series. So in the previous episode, we learned about file descriptor exhaustion, how to troubleshoot it and make sure your code is in check and doesn't cause the file descriptor exhaustion. So in this episode, today we will be hunting a new villain, a runaway CPU usage, the kind that makes the server feel like it's on fire. So today we will learn how to identify, diagnose, and fix CPU spikes like an SRE. So before touching any commands, here's the troubleshooting flow that experienced Linux engineers follow. So first, there is a high CPU utilization observed. We notice a high CPU usage. So we determine whether that CPU usage is from a user space, your code, or kernel space, the operating system. Then we identify the offending process which is responsible. And finally, we find why that process is burning CPU. So if you keep this flow in mind, if you always follow this, you will never panic during a CPU spike. So let's understand what user CPU and system CPU is. So user CPU means the time spent running your code. Things like loops, calculation, JSON parsing, application logic. And system CPU means the time spent running kernel operations, handling system calls like file input output, networking, memory allocations. How do you identify if it is a system CPU or a user CPU, right? That is also important. So we will we can see that in the top command. I'll show it how to identify that. So now, for example, if we run the top command in our console, so here you can see these, right? US and SY. So these are related to user CPU and system CPU. So here itself you can understand if the CPU is coming from a user, that is an application code, or a system call. So knowing this direction saves hours of guessing. So first, when you see there is a CPU spike, you first need to understand if it's coming from the user CPU or a system CPU. This makes troubleshooting more easier. So if going with the user CPU, if the user CPU is high, the this one, the problem is inside the code, not the OS. So for example, if you see this snippet, you are seeing 90.0 US. It should appear over here, right? So this is 90% is app code looping. So here itself you should understand that it is something to do with the app code. And the application can be any of your application. It can be a Node.js, it can be a Java, it can be Python a while true pass, or a Java garbage collection, buggy infinite loops. Such can be the cases for user CPU. And how to detect the system CPU? As we just saw, you need to look for this one. So now it is to 1.8 system CPU. So if this one, if %SY, that is 1.8, or numbers over here are high, the kernel is doing something heavy or stuck. So for example, if you look at this snippet, that is 85 for system CPU, the system is in pain. Something related to IO operations or system calls, you need to means understand that. So here our understanding should be clear. First, you need to understand what is higher, the system CPU or user CPU. So how to identify user versus system CPU we just saw. That is, we need to run the top command. We need to see these columns for user CPU and system CPU. So let's understand also a few other headers that are there, which will also be helpful. So this one, as you saw, it is user CPU. SY is for system CPU. Nice is like how to renice the process priority. That is, every process has a priority. So this is for that. So ID is for idle. WA, that is IO wait. We just learned about it in our first episode, how to identify IO wait. So this one will give you the IO wait. and HI is hardware and software interrupts. And then there is ST, that is stolen CPU. If there are VMs running on your machines, the CPU that is being used by VMs, that column also you can see. So we will just start with a small demo. So to learn CPU troubleshooting, we'll try to create a real issue. So we'll run a tiny Python program that does absolutely nothing forever. This is the classic mistake. Developers accidentally write infinite loop. So we are just trying to simulate that. So let's go ahead and run the demo. Okay. So we'll do a Python and we'll just pass on a while loop, which will just execute a infinite loop and hog the CPU. So it is running, the loop is on. So in the meantime, we'll just open a new terminal with with another session and see how the top command is behaving. It is at the CPU is at the as we just saw in the previous section, right? We need to see if it is a user or system CPU spike. So here you can clearly see it's a user one, right? It is an application that is having an issue and it is causing a maximum hog of CPU. So if you expand this, you will see it's 50 at 50 the CPU is at, and the command also is having Python here. So now if you see the CPU and if you see the cores, only one core is used up. The second core might also be used up if it was a multi-threaded one. So we can easily identify that one of the cores of the CPU is at 100 and it is a user it is the application code that is causing trouble and not the system one, because this column is showing up with 100, and that's a clear indication that's a application level issue, not a system level issue. So as you can see, it is a single threaded one, so only one of the cores is showing up. If it was multi-threaded, the other cores also would have been occupied. So currently we have only two cores and only one of the cores is being occupied. So this top command is really helpful when it comes to quick detection, but when it comes to deep diagnosis, you will have to use a PS command that we'll check next. So let's check the PS command. So to dig deep and to dig further to understand what is the exact cause of this high CPU, let's use the PS command. So we'll just do a PS minus EO, PID, PPID, PCPU, COM. We'll sort by PCPU and pipe head. So this command sorts all processes by CPU usage from highest to lowest. As you can see, Python 3 that we are just looping with an infinite loop is the culprit over here. And it is hogging 99.9% CPU. It gives you the process ID and the parent process ID. So PID will be your process ID, PPID will be your parent process ID, and PCPU is the CPU that will be your percentage of CPU time used. And command, of course, the command that is causing this high CPU or the CPU hog. So this way, this gives you a deeper understanding of what is happening. So top will help you to detect the process that is causing a high CPU, or it will help you identify if it is a system level CPU hog or user level application level CPU hog. And then PS command will further drill down what exactly the process is and how much is the CPU percent plus the process ID that is causing this hog. So let's move on to another command, that is pidstat. So top and PS, as we saw, are amazing starting points, but they show just a moment in time, real-world CPU spikes often appear for a split second and they just disappear. So this is where pidstat becomes a superhero because it lets us watch CPU usage every second over time and even drill down into CPU usage per thread. So let's see. So our first use case will be to track CPU consumption over time using pidstat. So we have the dumb simulation that we are using as we used previously, a Python infinite loop that is running. So let's see how pidstat helps us. So let's get out of the top command and I will do pidstat minus u and 1. So this command shows CPU usage every 1 second, helping us detect CPU spikes that come and go quickly. So if a process periodically hits 300% CPU every 5 seconds, pidstat will catch it. So if you can see the pidstat here, it is giving you the process ID and this being a application, so it is showing user space and it is consuming 100%. The command is also being shown, Python 3. And this you are getting every 1 second. So next use case we will see is to see CPU usage per thread. So in a multi-core CPU systems, a multi-core CPU allows applications to run multiple threads in parallel. So a process might look fine from outside, like it might show 30%, but inside, one thread may be burning the entire core. So pidstat exposes thread level CPU usage, something top cannot show clearly. So let's see this through a demo wherein we will have a multi-threaded application. So now we simulate a real production bug, 5 threads running inside a Python process, but only one of them goes into a CPU burning infinite loop. So we will be running this program. So this will be running around 5 threads and only one will be consuming the CPU. It will be hogging the CPU. The others will be in sleep mode kind of. Yeah, so what this will help us understand is we used pidstat before just to identify the process. But in some cases where the application is using multiple threads inside it, you need to understand which thread is hogging the CPU. Just just using top and PS gave you the application that is consuming the CPU, but it also becomes important for an SRE or a sysadmin to identify the root cause, like which thread among the processes consuming the maximum CPU kind of. So in such cases, pidstat becomes handy. So let's run the program. So here is the program that we are just running. This is running and let's open another terminal wherein we'll just so now just let's run the top command and see what the top gives you. The top has given you it is a user space application that is having issue, not the system level. So this will give you only the program that is having maximum CPU. So Python 3 is the program command that is being shown as seen in the screen. And also we have 2 cores. So one of the CPU cores is being used here. So this being a multi-threaded one, the load will be on both cores, but the maximum is on the CPU, one of the CPUs. So after this, let's also use the ps command and see how it is giving us the number of the highest hogging process. So this will give you the Python 3 application that is hogging the maximum CPU among all the processes that are being run on this system currently. So this was very straightforward to find, as we saw in our previous explanations of PS and top, how we found out the process that is hogging the maximum CPU. But here we are going in further and finding out the thread in the application that is consuming the maximum CPU. So here we will now use pidstat to expose the hot thread. So, so what pidstat we will do is it will give you the thread also, the threads that are being used to consume the CPU. So we'll just do pidstat. So it will give you, let's see is what it is giving. We'll just grab the process ID that is 1983 and just run this. So as you can see, it is giving us all the threads that belongs to this process. So let's pause it for some time and just go through the output. So what it is showing is it is giving you the main process ID and then the thread IDs. So all these are thread IDs 1, 2, 3, 4, 5. So now you must be wondering why there are 6 threads shown. Why we are seeing 6 threads when we should see 5. Because Python always creates an extra internal thread even when you start your own. So that is one of them. So this one will be your 1983 will be your thread ID, main Python application thread, and this one will be your hogging one, the CPU hog thread, and then these among them, the 87, 86, 85, and 84 will be your sleeping threads. So we have identified the hogging thread as well among this application using pidstat. So now let's see how we can do that and use strace to dig further and see what strace brings to the table. So what we will do is we will do sudo strace -p and grab the hogging thread ID 1988. So these are the logs that it has to show. So the thread is looping endlessly around a mutex. It keeps trying to sleep and then instantly it is waking up and it is retrying repeatedly. So it's a classic busy wait log bug. It is wasting CPU without performing any useful work. Now let's see how the output is for the one that is sleeping. So let's see the sleeper thread. Let's grab the sleeper thread, one of the sleeper threads 1987 and do sudo strace -p. So if you see, if you compare them, the output is different. So it is doing a p select over here. The thread is sleeping, waiting, not using any CPU. If you see, if you text wait, it is again waiting for lock, waiting to be woken up. And then you see the e timeout, that is the wait has expired. So this is a good behavior, a properly sleeping thread consuming almost zero CPU. So the CPU hog thread is consuming the maximum CPU, whereas these ones are not. You can identify it from the strace command that we did. So this becomes very useful when you are digging deep and finding the actual root cause in an application. So this will help you in real production scenarios where you will be asked to find out the issue in the application, and then you can drill down and give it to the owner of this application to tell them that this is the thread that is consuming the maximum CPU. You need to work on your code so they can then rectify that issue. So this way we use pidstat and strace to find the root cause. So this is exactly how production CPU incidents are debugged. So just not by using top and PS, by using top and PS, we just found out the process that is hogging the CPU. But then using pidstat, wherein we use the minus T to also show us the threads that are hogging the CPU. You found out the thread that is hogging the maximum CPU, and then strace helped you to find out the issue in the code as well. So this is a complete end-to-end approach that we saw. So this end-to-end approach turns CPU debugging from guesswork into a deterministic science. So we can catch misbehaving threads, infinite loops, log contention, application bugs, and more. So without reading a single line of applications code. So without doing anything, without reading, we at least got the root cause here, right? And then again, you can always check the code and see what the thread is doing, like how we just did the demo. We just created a demo, simulated the process, and then that piece of code wherein we had written a CPU hog, that was the culprit. So things would be different in production scenarios, but yes, this is a starting point for you guys to understand how the CPU debugging is actually done. So this level of visibility always helps SREs to fix performance incidents with confidence. There is no guesswork involved here. So guys, before we wrap up, here's the one thing I want you to take away. CPU debugging is not guesswork. It is a structured process. Start with the big picture using top. Top will let you know if the CPU is high. It is a system CPU or user CPU. That one distinction already tells you if the problem is your app or the kernel. Then zoom in using the right tools, PS and top. They help you identify the exact process and thread. pidstat fills the most important gap that most beginners miss. CPU over time. CPUs spike fast and disappear fast. Snapshots lie, but trends don't. Once you have identified the noisy thread, attach a strace. This is where the story unfolds. Is it looping? Is it stuck or on a Futex? Is it waiting on IO? The behavior always reveals the root cause. We also learned how system level CPU is very different from application CPU and how to simulate both. So debugging CPU is not about memorizing commands. It's about connecting the dots from the spike to the thread to the system call to the actual bug. And once you understand this mental model, you will stop fearing the CPU alerts and start treating them like puzzles you can solve confidently. So that's it for this episode. You now have everything you need to debug real CPU issues like a experienced SRE or a sysadmin. Thank you.